Hey there, and welcome to this explainer on the foundations and applications of nuclear chemistry. When most of us hear the word nuclear, we immediately picture glowing green rods or dangerous radiation, right? But the truth is actually far more profound. This is the science that takes us all the way from the invisible microscopic building blocks of matter to the literal immense power that fuels the stars. Today, we are going to unlock the energy hidden within matter itself. Okay, so here's our roadmap for today. We're going to zoom out progressively. We'll start with the anatomy of the atom, move on to radioactivity and decay, and then hit nuclear fission and fusion. After that, we'll step inside a nuclear reactor and finally wrap up with some really cool real-world applications. All right, let's jump right into section 1, anatomy of the atom, zooming into the invisible. Before we can even begin to understand nuclear power, we have to get a grip on the incredibly tiny stage where all of this action actually happens. Every single atom is made up of 3 fundamental particles. Deep down in the center, the nucleus, you've got positively charged protons and neutral neutrons. And then, orbiting around that nucleus, you have negatively charged electrons. Now, everyday, ordinary chemistry, that's all about those orbiting electrons. But nuclear chemistry is a completely different ballgame. It is exclusively about what happens deep inside that nucleus. The number of protons gives us our atomic number, or Z, and that simply tells us what element we're looking at. Add the protons and neutrons together, and boom, you get the mass number, or A. Now, I know it is incredibly easy to get the terminology mixed up here, so let's cleanly separate these concepts with some real-world examples. If you have the exact same number of protons, but a different number of neutrons, you've got isotopes. Think carbon-12 and carbon-14, same element, just a different weight. Now, if you have completely different elements that just happen to have the exact same total mass number, those are called isobars, like argon-40 and calcium-40. And finally, if they have the exact same number of neutrons but different protons, those are isotones. So, you might be wondering, with all those positively charged protons packed into such a tiny, tight space, why don't they just repel each other and blow the atom apart? Well, the answer is binding energy. There's this absolutely fascinating phenomenon called mass defect. Basically, the actual mass of a nucleus is slightly less than the calculated mass of all its individual parts. That missing mass, it doesn't just vanish, it actually gets converted into binding energy. You can kind of think of it as an atomic superglue. It acts like a tightly packed spring, determining how stable the nucleus is based on the ratio of neutrons to protons. Simply put, the higher the binding energy, the more stable the nucleus. Okay, moving on to section 2, radioactivity and decay, when atoms break apart. So what exactly happens when that atomic superglue fails and an atom becomes unstable? Well, it essentially tries to find stability by spontaneously spitting out radiation. And we generally see 3 escalating types of emissions here. First up is alpha radiation, which is essentially just a helium nucleus. It has a really high ionizing ability, but extremely low penetration power. Like a literal sheet of paper can stop it. Second is beta radiation. These are high-speed electrons with moderate penetration. And third, the heavy hitter, gamma radiation. These are pure electromagnetic waves with extremely high penetration power. You need some serious heavy shielding to block these guys. Now, the absolutely crucial thing you need to take away from this is the sheer, unstoppable nature of radioactivity. Radioactive decay follows a strict exponential law. The rate at which it decays is entirely proportional to the number of atoms present. And here's the wild part, it is completely uncontrollable. You cannot boil it away, you cannot freeze it, and you can't speed it up by throwing in some chemical catalysts. It just happens, relentlessly. Because it is so wonderfully predictable, scientists use a measurement called half-life. The half-life is simply the exact amount of time required for half of a radioactive substance to spontaneously decay into something else entirely. The formula for this is beautifully elegant. The amount remaining equals the initial amount multiplied by 1/2 to the power of the number of half-lives that have passed. Just think of that simple fraction, 1/2, as this unyielding clock ticking away inside the element. If a substance has a half-life of, say, 1 year, then after 1 year, you have exactly half left. After 2 years, you have a quarter. It is a constant, totally measurable countdown. Which brings us to section 3, nuclear fission and fusion, the great release. All right, we've looked at passive, spontaneous decay. Let's ramp up the energy now and talk about active, explosive nuclear reactions. See, while ordinary chemical reactions just shuffle electrons around, a nuclear reaction violently changes the nucleus itself. The equation for this is simple, but it is incredibly powerful. You take a target nucleus, you smash it with a projectile, and what do you get? An entirely new product, plus a truly tremendous release of energy. The big takeaway here is understanding the two fundamentally different ways this massive release of energy happens. On one side, we have fission. This is the splitting apart of a really heavy nucleus, like uranium-235, into smaller nuclei, like barium and krypton. This is the process we harness in nuclear reactors to power our cities. On the completely flip side is fusion. This is the exact opposite. It's the mashing together of extremely light nuclei, like hydrogen, to form a heavier nucleus, like helium. Now, fusion requires unimaginably high temperatures. We're talking star-level heat here. In fact, it's the literal process that powers our sun and lights up the entire universe. Let's move to section 4, inside a nuclear reactor, harnessing the beast. So, how do we actually put this to use here on Earth? Let's take this explosive science and ground it into some practical engineering. To generate electricity, we literally have to tame that fierce fission reaction safely. Let's actually build a reactor in your mind right now. First off, you need the fuel, typically uranium-235. Next, you need a moderator. Fission releases these incredibly fast neutrons, but to keep the chain reaction going, we actually have to slow them down. That's exactly what the moderator does. Then, you insert control rods. These guys absorb neutrons to perfectly regulate the speed of the reaction so it doesn't get out of hand. And finally, you pump in a coolant to draw away the massive amounts of heat being generated. That heat boils water, creates steam, spins the turbines, and boom, electricity. Now, obviously, dealing with these kinds of materials comes with some huge responsibilities. Exposure to radiation poses very severe biological hazards. We're talking cell damage, cancer, and genetic mutations. Because of this, incredibly strict safety measures are absolutely non-negotiable. Plants rely on heavy lead and massive thick concrete shielding to block harmful rays. They enforce strictly limited exposure times for any personnel working there, and they rely on highly regulated, long-term safe disposal methods for all that spent radioactive waste. This naturally leads to a really complex debate globally when it comes to nuclear energy. Let's just neutrally look at how the facts weigh out. On the pro side, nuclear energy provides a staggeringly high energy output. It acts as a highly reliable baseload power source, meaning it runs 24/7. And it does all this with very, very low greenhouse gas emissions compared to fossil fuels. But on the con side, the financial cost to actually build these plants is exceptionally high. There is an ever-present risk of severe catastrophic accidents, and we are left with the long-term burden of figuring out how to safely store that radioactive waste for centuries. The science itself simply provides the capability. It's up to society to weigh these outcomes. And finally, Section 5. Real-world applications, the everyday impact. If we zoom all the way out from the power plant, you'll see that these invisible atomic forces do way more than just spin turbines. In fact, the exact same underlying science used in a nuclear reactor is probably quietly at work in your own community right now. In medicine, targeted radiation is an absolute cornerstone of cancer treatment through radiotherapy, and it's completely essential for precise medical imaging like PET scans. Even in agriculture, we use nuclear chemistry for food preservation, safely extending shelf life, and for highly targeted pest control that protects our crops without needing harsh chemical pesticides. And it doesn't stop there. The applications continue right into industry, where engineers use radiation to get highly precise thickness measurements in manufacturing and for advanced leak detection in deep underground pipelines. And incredibly, by relying on that constant ticking clock of the half-life we talked about earlier, archaeologists use carbon dating to determine the exact age of ancient artifacts. It literally allows us to accurately map human history. How cool is that? Bringing this all together, our source material sums up this entire micro to macro journey perfectly with this quote. Nuclear chemistry is not just about atoms, it's about understanding the immense energy hidden within matter. From the tiniest invisible subatomic particles to the forces that light up our cities and save lives in our hospitals, this field really does represent a profound understanding of our universe. It is undeniably one of the most impactful branches of science shaping our modern world today. It offers incredible, almost limitless promise for medicine, clean energy, and industry, but alongside some very heavy responsibilities. So we've successfully unlocked the immense energy hidden within matter. But looking forward to the next generation of discovery, how will we choose to use it next? Thank you so much for exploring this fascinating topic with me. Keep learning, and I'll catch you on the next explainer.